Hello, this is Group Nine's Thermodynamic Project. I'm Austin Bone, and for our topic, we decided our problem statement was how does a standard refrigerator keep items cold? And to answer that, we will be using the vapor compression cycle of real refrigerators, and we will explain why this cycle is implemented in refrigerators and how the process within the vapor compression cycle successfully keeps items or people at the proper temperature. The vapor compression cycle can be found in refrigerators, transportation vehicles, and even in air conditioners. Let's see. The vapor compression cycle is widely used because it is more efficient, allows for a wider range of versatile refrigerants, it's cheaper, and requires less maintenance compared to other refrigeration cycles.
My name is Ian Bell, and this slide will show the basic idea behind how a standard vapor compression refrigeration system works. The cycle has four key processes. The first is compression. The refrigerant enters the compressor as a low pressure, low temperature vapor. The compressor raises both the temperature and the pressure, so it leaves as a high energy superheated vapor. The next will be condensation. The hot water that enters the condenser where it releases heat to the surroundings. This is the Q hot in this diagram that you can see. As the refrigerant loses heat, it changes phases and exits the condenser as a high pressure liquid. Then we have expansion. The liquid flows through an expansion valve where the pressure drops suddenly. This drop causes a large temperature decrease due to the Joule-Thomson effect, producing a cold mixture of liquid and vapor. Finally, there is evaporation. The cold mixture enters the evaporator. Here, the refrigerant absorbs heat from the environment, and this will be Q cold that you can see. As it absorbs heat, it fully vaporizes and becomes slightly superheated again. That vapor then returns to the compressor and the cycle repeats. Overall, the system moves heat from the cold reservoir to the hot reservoir using work input from the compressor. Next to go in more in depth about this vapor compression cycle will be Tong. Thank you.
As Ian mentioned before, there are four processes to the vapor compression refrigeration cycle. Ideally, the system assumes no losses or inefficiencies. The compressor is adiabatic and isentropic, meaning no heat is lost and the work required is simply the difference between states 2 and 1. Heat is rejected to the condenser at constant pressure, and the expansion valve is isentropic. In the evaporator, heat is absorbed at constant pressure, and the ideal coefficient of performance is the heat absorbed in the evaporator divided by the compressor work input. However, real world systems behave differently due to irreversibilities like fluid friction and um, heat loss to the surroundings. In the actual compressor, the process is no longer isentropic or or um, or adiabatic because the compressor heats up and requires more work than the ideal case. Pressure drops and the heat transfer to the environment also occur in both the condenser and the evaporator, reducing their efficiency. The expansion valve remains isentropic, but the pressure drop is harder to control. As a result, the actual COP becomes a ratio of reduced cooling effect to the increased compressor work. Overall, these real-world losses mean the actual COP is always lower than the ideal COP, and the difference reflects the impact of system inefficiencies and energy losses.
Hello, I'm Alex, and I will go over our worked example and our conclusion. The problem statement provided gives us the information for a refrigerant working through the vapor compression cycle. The given values are from state 1, which is the compressor inlet, and state 3, which is the condenser outlet. Using these values, we can find the enthalpy and entropy at state 1 and the entropy at state 3. For an ideal refrigerator, the entropy does not change when passing through the compressor, as this is an isentropic process. Using this knowledge, we calculate the ideal enthalpy at state 2, which is the compressor outlet, where the refrigerant is known to be a superheated vapor. We use all of the values that we have now to solve for the coefficient performance of an ideal refrigerator, which is roughly 4.1. From the equations for isentropic efficiency of a compressor, we solve for the actual enthalpy at state 2. Using this new value, we can find that the actual coefficient of performance for an actual refrigerator following the vapor compression cycle is slightly less than 3.5. This decrease shows us how assuming ideal conditions minimizes the work input required for the refrigerator. To conclude, the vapor compression cycle is a well-known refrigeration cycle that we encounter in our everyday lives. Some important results from our research are that refrigerators do not occur in nature, as this would violate the Clausius statement, a statement of the second law of thermodynamics, which states that heat cannot of itself flow from a hotter to a colder body. Another key point is that ideal refrigerators following the vapor compression cycle are not the same as Carnot refrigerators, as Carnot refrigerators do not include a throttling process, which is an irreversible process. This means that ideal refrigerators following the vapor compression cycle are not reversible, but they are still ideal. And finally, actual refrigerators involve the irreversibilities found in nature, such as friction, but they still follow the processes of the vapor compression cycle. Thank you for listening, and I hope you enjoyed.